we consider special relativity, we have to talk about Newtonian theory. We can specify an event using a system of 3 position coordinates, x, y, and z, collectively known as space, and a time, which is a clock or a series of synchronized clocks. This is all defined with respect to a frame of reference. A frame of reference consists of this system, an origin, and an observer. These frames can have velocity and different orientations from one another. Inertial frames are reference frames in which Newton's first law holds. Therefore, they must only have constant velocity and move in a straight line. So 2 inertial frames can only differ in terms of velocity and angle. The principle of relativity states that the laws of physics are the same in every inertial frame. No exception to this has been found, so this is true for both Newtonian theory and special relativity. In Newtonian theory, time is absolute, which means it is the same for every inertial frame. Let's say we have 2 inertial frames, S and S prime. They are in standard configuration if they have the same origin at t equals t prime, which equals 0, and S prime is moving with constant velocity v along the positive x-axis. We have what is called this Galilean transformation between S and S prime, relating their coordinates. How exactly one derives these equations is a bit complex, and I won't talk about that for now. If we have 2 frames in an event, applying the Galilean transformation results in the 2 frames having different coordinates for the event but at the same time. This is called separately invariant because changing the position of the event is separate from the time and vice versa. Therefore, space and time are considered separately. In special relativity, instead of time being the same in all inertial frames, the speed of light c is the same. If we have 2 frames in standard configuration and a photon is emitted from the origin traveling in any direction, the distance between the coordinates of the photon in the 2 reference frames must be 0. We obtain what is called the Lorentz transformation. Notice that the Lorentz transformation reduces to a Galilean transformation when beta is much less than 1. The interval between 2 events is defined using the Pythagorean theorem. Light cones tell us how to treat an interval. Take event A. If the interval between 2 events is greater than 0, it is considered time-like, or the events are separated in space. So the interval between A and B is time-like. If it's equal to 0, the interval is null or light-like, just like the interval between A and C. If the interval is less than 0, it is considered space-like, and the events are separated by time. So the interval between A and D is space-like. We can visualize this using space-time diagrams, which show the coordinate transformation of an event between 2 frames. A consequence of the Lorentz transformation is length contraction and time dilation. If a rod at rest in S prime with length L0 extends from XA prime to XB prime, we apply the Lorentz transform to see what the rod looks like in frame S. The observer at S prime measures XA prime and XB prime simultaneously at a predetermined time. So T equals TA prime, which equals TB prime. We get that the length of the rod with respect to frame S is smaller by a factor of gamma. The same argument can be applied to time dilation. If a clock at rest in S prime ticks at time TA prime and TA prime plus T0, we can apply the Lorentz transformation. Since the clock is at rest in S prime, XA prime equals XB prime. We can subtract and find that the clock moves slower by a factor of about 1 minus beta squared to the 1/2. We can visualize both of these effects using a space-time diagram. If we plot the equation c squared times t squared minus x squared equals c squared t prime squared minus x prime squared equals plus or minus 1, I get a hyperbola. What this shows is that if you travel a unit distance along a position or time axis, the transform of that distance will not be the same. The distinction between special and general relativity is that special relativity does not deal with gravity and acceleration, but general relativity does.